In this tutorial script, we're now going to run something that looks very similar to scenario basic orbit, but instead of just having Earth and have the Earth be at the origin of our inertial frame, we're actually going to have Earth, Sun, Moon, and Jupiter, because why not, right? So it's actually going to solve a full multi-body problem. So we're going to show here how we're going to have to modify the script to make our spacecraft subject to multiple gravity bodies, and these gravity bodies have to have specific locations. And that's going to be given through the SPICE interface. SPICE is a JPL software library that's open source. You can download, and we've included it in Basilisk. So you can give it a time, and it'll tell you this is where Jupiter, Mars will be. And in fact, it also tell you what the orientation is. Here, we don't need orientations, just the positions. But so when we run SPICE interface, when we create these planets, we need to make sure that the positions of the planets are specified by SPICE. And when the gravity effector pulls all those in, every update, it needs to know where's Earth now, where's Mars now, and that will be the simulation. When we run it, we'll actually run SPICE twice, once in C code in Basilisk, in that SPICE interface module, but we also run SPICE independently in Python to kind of do a validation. And we'll simulate the Hubble motion here, and we will be able to show this output that the Basilisk result and what the actual Hubble orbit looked like is very, very similar. You have to really zoom in to start to see a difference. Here, we're just doing gravity, but of course, the real Hubble would be exposed to solar radiation pressure and different drag forces and stuff. So we're not including any of those things here. But this is kind of a nice validation, but also an illustration of how to do multiple gravity bodies. Well, let's switch over to our Python script. So this is scenario orbit multi-body. Again, it's going to be a Basilisk script with a single process, a single task. That's what you're going to see here. We create our process, and we add a task. We're going to run it here every 5 seconds. Just trying to get a little better accuracy than every 10 seconds we did earlier, but it still runs pretty fast. Then we make our spacecraft, give it a target, and I add the spacecraft Basilisk module to our task. So it will get executed every 5 seconds and integrated forward. You notice here, I'm also giving it a priority. So it actually has priority 1. Other modules won't have a priority. So this one will run first, and then it updates all the planets for the next time step. We wanted to update the planets after we integrate the spacecraft. If we do it before, the planets would be one time step ahead of us already. So here it was important that we make sure the spacecraft is executed first, and then SPICE interface is called afterwards to update for the next time step. So how do we do this? We're going to use our handy dandy gravity body factory class, right? Like before. We want to make Earth, Mars, Sun, Moon, and Jupiter. We could have called create Earth, create Mars barycenter, create Sun, create Moon, all individually, or there's this convenient function called create bodies. If we go look at that one in the sim include grav body Python file, you give it a list of names, strings, and it just matches the strings. And if it's Mercury, it will say, it will actually call and execute for you, create Mercury, create Earth, create Moon, create Mars barycenter, and so forth. So it's just a convenience. Instead of doing all these line by line, you can do it all in one line. Coding preference, up to you. Now this one does return the grav bodies, which is the dictionary list in Python. So this handle here is actually a dictionary list. So now if we want to set Earth to be the central body, so when we set the spacecraft position and velocity, the initial position velocity to initialize the dynamics, we can go to the dictionary list, select the Earth element, right? And then for that element, set is central body equal to true. So it's just different ways of dealing with it. You could have used create Earth like before, and then did create Mars and everything, and then within the Earth do is central body. So I'm just trying to show you different ways to do it. Oh, here we go, actually. Here's an example where I'm actually giving you in the comments a different way to do it. Then for the Earth, we want to use spherical harmonics. We're actually going to load them up, a different file than we had in the earlier example, because we're going to go up to 100th order. So this is going to be a pretty accurate gravity field model that we're going to include here in this case. So now we have 1, 2, 3, 4, 5 gravity body problems. Earth is subject to spherical harmonics. We use the same line here to connect the list of grav bodies to the spacecraft gravity field that we need to specify. And so nothing has changed there from earlier simulations. Now, next, with SPICE, we need to specify when is this simulation happening? What's the epoch, date, and time? Because the planets will be in different position in March versus April versus December, and what year and what time, right? So here, I'm going to show you how to do this. There's one easy way. You can just make this string, 2012, May 1st, 28.5 minutes after midnight. That's going to be our initial epoch. And there's also a SPICE string format. These two lines here, this is all actually only used for the Python version of SPICE later on in the code. If you're wondering why do we have this here, because other code that runs SPICE doesn't do this. That's the only reason we have those two lines. So really, to specify in the Graph Factory and create a SPICE interface, there's again a convenience function that does a lot of the magic for you. You can look at it and we'll see and highlight it in a second, but I do recommend you use this. So in the Graph Factory, if you say create SPICE interface, it will actually create the SPICE module. It knows which planets we have set up. It's going to connect SPICE with the right names to these planets and then connect the gravity body data, the things we'd have from create Earth. There's actually an input message there that says, where is the Earth? And the output of SPICE will be where the Earth is. So it'll connect those two things up. So every update cycle, Earth's position will be increased to the next time step. We give it a time string. That's critical. It needs to know in SPICE what is the date that we're going to simulate. And we also then have an epoch message that's a flag, and we're setting it to true. So in SPICE, you can actually specify the epoch time directly, or in the SPICE interface module from Basilisk, you can also have an input message that specifies the time. My preference is to use the input message because there's other modules that might need epoch times. Magnetic fields sometimes depend on time. Neutral density models from atmospheres might depend on time. And if you specify them individually in each module, it's up to you to make sure they're all in sync. Otherwise, you're pretending that planets are in March, but magnetic fields acting like it's in September. So maybe you want to do that, and then you do it individually. Here, I prefer to read all the information in from a message, because then I can create one message and just connect that message to all the modules that need the time information for epoch. So I set this flag to true. It's my preference. But let's go look at what this one actually does. So the create SPICE interface, it's part of SimInclude Graph Body. And it's another convenience function to help you just set up the SPICE interface. You don't have to do it all from hand. These are optional flags if you want to specify the planet names or SPICE names, all this stuff. You can do that. So you can read through here. If you know a lot about SPICE, you'll recognize what's happening here and the coordinate frames. The main things I want to go through is you can see inside the factory, it's creating Basilisk SPICE interface module. So that makes, like the spacecraft module, it's making a SPICE interface module, giving it a tag. We have to specify the path for the data. So that was something that was provided here as one of the arguments, including the time was one of the arguments, and we're going to set that time. And we have to add all the planets names, and those we fortunately have already. SPICE planet names have been set up earlier when we created Earth, Mars, Jupiter, and so forth. Let's see, the rest is just if you have particular kernels of planet frames. What's interesting here, this is an important step where we actually loop through, and we're gonna, for every gravity body item, so grav bodies is that dictionary list. So we're pulling out every one of those Earth, Sun, Moon, Mars, Jupiter gravity body elements. And part of that grav body data class is there's an input message. And we said if the input message is not connected, that planet is just going to be at the origin, 000. Here, per planet that you set up, it's actually subscribing that planet to this Basilisk SPICE interface module, which we called, up here, we called it SPICE object. And its output messages, it's a vector of output messages, are called planet state out messages, and they're in sequence. So if the first, this is an ordered dictionary list. So if the first element is Earth, then the first element of the SPICE output messages is going to be the Earth's one. It's going to be created in sequence here. And so this is what connects the SPICE ephemeris planet information as an input message to the grav body data that the spacecraft needs to figure out what is my gravity relative to Earth, Moon, Jupiter, and so forth. The last few lines, if we have this keyword epoch in message set, it actually creates an epoch message. So first it does a conversion that it needs to do. This is a convenience function that turns this time into the epoch message type that we need, and it will return that message handle. So we can look at this quickly if you really want to get into it, but it converts this to Gregorian, which is what we usually set up. In the epoch message, we set up a year, month, day, hours, minutes, and seconds. Seconds has fractions in it. Everything else is, I believe, integers. And it creates the message, and this owns itself, so others can edit this message outside again. So this is kind of what's happening here. And we use some Python SPICE routines to do all these time conversions from different string formats, which has been really handy. So anyway, so here we've created the message, we stored it inside the Graph Factory, and so that's going to be there. And then the SPICE object, that's the SPICE interface Basilisk modules, epoch in message subscribes to this standalone epoch message. This is where we connected now. We're running on May 12th, 2012, whatever the date was. I forget. May 12th, May 1st, 2012. That's where it sets it all up. Okay, a lot of talking, but basically this is now, you can see it's a really easy, for most of them, people just run the data from Basilisk that we've provided. They have the path is the same. You set up your string, set this in, and it does everything for you, and you're good to run. So good. Now we're ready. So we got SPICE up and running. When we're logging, SPICE's coordinate system is actually the sun, the heliocentric coordinate frame, which is at 0, 0 in the middle of the sun. We don't want to get our positions of the spacecraft relative to the sun. They would be 149 billion meters in some direction, because then you have to get the Earth position and subtract it and do all this stuff. So there's a convenience thing here that you can tell SPICE, you can set a 0 base and say that's Earth. So now when it outputs all the positions, it's not relative to the sun's heliocentric origin, but it uses the Earth as the origin for any position vectors. And that'll be easier for plotting purposes and when we compare. So that's what the 0 base does. Now, the SPICE object, the SPICE interface module was created, but we still have to add it to a task. So that's what this line does. And because it was created inside the Graph Factory, it is graphfactory.spice object. Kind of makes sense, right? That's inside that one. So now we have everything set up. The rest of this stuff, this is all code that actually sets up and runs a Python version, PySplice. It's Python Spice. Gosh, I can't talk. And we want to compare the JPL's SPICE Hubble Space Telescope ephemeris or trajectory with or the New Horizons. You got two options. I'm going to show the Hubble one here. So what does the actually recorded Hubble trajectory look like, and what does our trajectory look like? And this is a nice validation that hopefully this code is all set up to work properly and we get something very similar. So that's what all this code does. It's purely for comparison purposes. Normally, if you do a Basilisk sim, you wouldn't be running this. Now we need initial states. So we're actually running the Python version of SPICE for this SPICE name, which would be Hubble. It's going to pull at this time, where is it, and relative to the Earth, because those were the initial conditions, right? We're setting here where we set is central is set to Earth. So the initial position should be set relative to the Earth. That's why this part is important. Again, this is just for comparison. But now we have an apples and apples, the same position velocity at this time and date as SPICE uses. We're also using a Basilisk. Now we want to forward integrate. The rest of it, we're running for 2000 seconds. We're recording 50 data points. We're setting up our recorders. The enable visualization is pretty basic, that usual stuff. We initialize the sim, configure a stop time, execute, right? Standard stuff now. Then we can pull the data and plot and then see what happens. And this does all the comparison plotting and pull, it uses the Python SPICE to plot the actual Hubble one that's recorded and compares to the Basilisk Hubble motion. If I run that, script, goes pretty quickly. You get a bunch, this shows the differences. It's only off by, tens of meters after this time. And again, we don't have drag, we don't have SRP, which is just gravity. This plot's kind of nice because it will show you kind of, this is pretty darn close. You really have to zoom in to see the difference between basilisk and spice. They're kind of right on top of each other, as you'd hope they would be. So that runs that script. So what are some highlights here? You can add multiple gravity bodies. Instead of doing create Earth, create Mars, create Moon, you can also create a bunch of them together. But you must specify then where is each one of these gravity bodies. And here I'm showing you an example where we're using SPICE to tell you where are these planets. And this is where you connect them. There are other things. There's a planet ephemeris module that just assumes you specify orbit elements for the planets, and then it just uses Keplerian motion. Not quite as precise as SPICE, but much faster. And it might be simpler to set up if you're doing a lot of what ifs yourself instead of setting up a SPICE kernel. So there's other ways you can specify positions of planets and connect them. Here, I'm just showing you how it's all done within the SPICE framework. This is used a lot. And then we recorded all relative to the Earth. Hope you enjoyed. Have fun playing with this.